let me get this up. So we are going to be doing some word problems, but the way that we're setting it up is going to make so much more sense today. So you guys remember last week, you guys had there was a page of word problems that we had to do, and it was like, the cars, this is this much, and every week they reduce the price 10%, right? And so last week, the trickiest part, I think, for people was deciding like the rate. Do you take the decimal and do you make it 1 point the decimal, or do you subtract it? That was the kind of the part that confused people, and what we're going to do today will help that make more sense. All right, but we're going to review real quick what growth looks like with our graphs and what decay looks like, just because we've seen all the different kind of things happening with our graphs. So you're just going to make like a rough sketch of a coordinate plane. We're going to have 2 of them. So just do like a little rough sketch. One side, the left will be our growth, the right will be our decay. So remembering that we read graphs from left to right. So for our growth, it would have looked like this. And this is just like an example. It does not have to be perfect. What you want to have is, if you guys remember when we were looking on the graphing calculator yesterday, how some of our curves, well, all of them actually got close to the x-axis but never touched it. So you want to make sure that's happening over here. So it looks like it's getting close to the x-axis, never touches it, and then from left to right moves up. And it's going to seem kind of strange, but below the x-axis, we're going to draw what growth would look like, and it's actually a mirror image. I'm putting it in with a dashed line just so that you can see that they're 2 different curves. So even though this looks like from left to right my curve is going down, because it's moving away from the x-axis, this could also be considered growth, even though it feels kind of strange. I'll put it better in words in just a second here. Okay, so this is going to be growth. And in case you didn't remember or didn't notice, growth happened when the b was greater than 1. So when you were graphing your exponential functions, whenever the b was bigger than 1, you got one of these 2 types of graphs. The direction it went, or which side of the x-axis it was on, depended on the a. Right? When the a was negative, it was this one. When the a was positive, it was this one. Right? A way to kind of put into words describing the growth curve would be, it starts at, so it starts close to the asymptote. If you remember, the asymptote is a line that the graph gets close to but never touches. So it starts close to the asymptote and moves away from it. So if you're reading it left to right, it starts close to the asymptote and then moves away from it. That's a growth. Same thing down below. It starts close to 0 and moves away. So basically as it gets further away from 0, right? Okay, so decay is going to be all the opposite, right? So for our decay, we're going to start away from the asymptote and move closer to it. So it would be like maybe something like that. And again, you don't have to be perfect. Just we want a curve, and we want that curve to get closer to the x-axis as it moves to the right. And then same thing down below. Starts away from the asymptote and moves closer to it. That would be decay. And if you think about the graphs, as time goes on, it's getting closer to zero, either direction. That's a decay. Okay. And so we're going to label this decay. And this is when B was between 0 and 1. With growth and decay, the B's, we don't have any zero or anything less than 0. Or we don't have any negatives. You'll see kind of why in a second. But, all right, so keep that in mind too. So this, putting this into words would say starts away, but moves closer to the asymptote. So it starts away from the asymptote and then moves closer to it as we go left to right. Okay. So there is a formula. And so what I want you guys to do for the next part is I'm going to give you the general like format, and I'm going to write it in the middle, and then I'm going to write a specific one for growth and a specific one for decay. So like when you lay it out, just kind of put what I'm about to give you in the middle. So it's going to look very familiar. With some adjustments. So we've got, y equals c times 1 plus minus r to the x power. So that's the general growth and decay function. And it does look really familiar. It should look just like, well, not just like, but really close to the format we've seen already, where we had f of x equals a times b to the x power. So in this case, the a is written as a c, and instead of a b, we have a 1 and a plus or minus r. The x is still the x. It is still the same exact function. It's just that when we have growth and decay situations, this part in the middle is actually going to help us make it a little bit easier than it was last week to figure out the b. All right. This is still considered our b inside here. All right. So this plus and minus, you guys have seen that before, right? With like square roots. You guys see that with square roots? They put the plus and minus in the front of it. If you haven't seen this before, what that means is it could be plus, it could be minus. So this is saying I could have 1 plus r or 1 minus r. Okay. And the reason that happens is because we need one for growth and one for decay. So the one for growth is going to be 1 equals c times 1 plus r to the x power. And then you could probably guess what the decay one would be. Y equals c times 1 minus r to the x power. Okay. All right. And you'll see in a second where that, like where the 1 comes from. All right. So let's just put some words to the different variables we see now. So our C replaced the A in what we've been working with, but it's still the same thing. It's still the initial value. Okay. So C is our initial value, or our y-intercept. Just like the A, right? Now in a sequence, when we first started talking about geometric sequences, that first term was the first part of our formula, but now that we've been looking, our actual initial value is our y-intercept, right? It's like the 0 term. R is our growth or decay rate. And we're going to write that as a decimal. The reason it'll be written as a decimal is because usually those are percents. Almost always percents. And then again, you'll see in a minute why we have the 1 there. And our x is the input variable. The y is the output. So like when they say how much is it worth after 5 years? The 5 is our input value, right? We replace the x with a 5, do the math, and figure out the value. Right? And once in a while, you're actually given the output value and you have to figure out the input, right? Okay. So we're just going to jump into an example. So let's look at example number 1. I'm going to try to trim the words down as much as possible here. So you deposit $100 in an account that earns 8% interest compounded annually. What that means is at the end of the year, they take 8% of your $100, and that's how much you have going into the next year. So there's some that are compounded monthly. So like at the end of the month, they'll say, okay, how much did you earn? And there's a whole big crazy formula. So compounded annually is like the easiest option for what we're doing here. Just so you guys know. All right. So how much do you have after 10 years? Okay. All right. Now, like I said, these are just like last week when we had the word problems. The only tricky part is, like, for the most part, people were able to find what the A was, and the rate was 8%, but we couldn't just make 0.08 be the rate. If you guys remember, we talked about it had to be like 1.08 so that you could include the original 100 plus the 8%, right? And that's what the formula actually does for us. The formula does that part that we had to think about for the rate. So the first thing we're going to do is identify everything that we need to identify. So the first thing is this a growth or a decay? A growth, right? So anytime, whatever we take what we start with, and whatever's happening in the problem, is it going to make what we start with get bigger or smaller, right? So if it's going to get bigger because we're earning interest, it's a growth. So just make a little note that it's growth. And really, we want to do that so we make sure we're using the right format of the equation, right? So we have growth. Then our C is our initial value, which is $100. Our rate is 8%. So it's 0.08, right? And our X, or our input value, so what we're going to put into the formula to figure out our answer is going to be the 10 years, right? And then all we do is we take the information, we plug it into the to the equation. Okay, so Y equals our initial rate. Now, the formula that we're going to use is for growth. So it's 1 plus R, right? To the 10th power. And that's why we have 1.08, which you might have already thought of as you were looking at the problem. So y equals 100 times 1.08 to the 10th power. I'll calculate that for you guys. If you want to open a Chromebook and grab a graphic or a scientific calculator, you can. Oh. So y equals $215.89. And with the money, you guys, if you want to round to the nearest dollar, you could do that, or you can leave it cents. So after 10 years, you only have $215 in your bank account. So that's one where, like, I guess you open an account and forget about it. Then 10 years later, you're like, oh, it's $215. Yay, it's for your kid. Yeah. Right. Yeah. If you put $100 in an account when they're born and then at 10, you know. Or if you start at 10, then yeah. Well, if you start at 10, they won't have to much. Right. Yeah. Yeah. So that would not be a good plan for college. And that's pretty much the process. So what's nice is that the 1 plus minus r part actually covers you from having to try to decide how that rate needs to be written. Kind of like when we did the math problem with the car. There was a used car lot that had a car that was valued at a certain amount of money, and every week the price dropped 10%. If you guys remember that problem, you had to actually make your rate 0.9, and it was a little confusing. So this actually takes care of that, right? And we're going to see that in this next example real quick. Okay, so example 2. You bought a new car, definitely not with a savings account from number 1, for $44,000. That's like probably like an SUV, like if you had like a third row seat type car, minivan, like a nice 4-door, like regular car. It's like a nice car for $44,000. I mean, nothing crazy. It depreciates. Now, depreciate means goes down in value, which is how cars work, unfortunately. Depreciates at 12% each year. Just in case you want to make a note about depreciate. So the value goes down each year, which is what happens. I mean, literally the minute you drive off a parking lot with a car you just bought, it's worth less than when you bought it. Cars are one of the only things that don't really like make you money. They're not a good investment like that. Unless you do like something crazy, like customization and stuff. But all right, so we have something depreciating, so this is going to be a decay situation, right? So let's make a note that it's a decay. And we know that because depreciation. Now, this is one of those things where if we were to look at this as just saying like, okay, well, if it depreciates 12% a year, if you were to do the math on that, so if you were to multiply 44,000 by 12%, so you can kind of understand what's happening here. So if we did 44,000 times 12%, that would be 5,000. I don't know how to, hold on. Let's do this. I just don't like that it's in scientific notation. Hold on. Should make sense because it's a scientific calculator. But 5,280. So if you were to look at this, it wouldn't be, oh, well, now it's worth 5,280 after the year. No, that's how much it decreases, right? So I have to subtract that from the 44,000. Okay, so I would have to subtract that from the 44,000 to get what it's worth, right? So instead of doing all that work, the formula, that's why we have the 1 minus the rate. So what's 1 minus 12% would be 88%, right? So if I took the 44,000 times 88%, I get 38,720. So this is actually what the car is worth the next year. So instead of having to go through all of that like logical kind of thinking in her head, that's why the formula is so nice, because the 1 minus the rate is already included. So you'll see in a second that 88% happens. So my initial amount is 44,000. My rate is 12%, 0.12. And the input value, oh, where's my question? That's the part we need. Sorry, guys. Find the value in 8 years. So our input is going to be 8 for the 8 years. So now because it's decay, we want to use the decay formula. So y equals my initial value times 1 minus 0.12 to the x power, or the 8th, right? And this 1 minus 1.2 is going to get us the 88%. So that gets us our 0.88 that we just did on the calculator. So again, there's really, in these kind of word problems, at least for today's stuff, all you really have to think through is whether it's growth or decay. Write out, organize the information you're given and then plug it in and work it out, which is really nice. This would have been nice to have last week when you guys did those word problems. So you end up with $15,823 and probably some cents, but you could just round to the dollar. The reason that would happen is because when you buy a car, like, they don't tell you how many cents it costs. They're all whole numbers. A bank account, you want to know to the cent how much money you have, right? I want to know that. I want that 89 cents, right? But with a car, nobody's telling you like the change for the car, all right? So that's it. It's literally all we have to do today, okay? So I'm going to give you